So first let us work some simple cases problem like this, then combination of these. Here only one sections are enough for solving this problem, one or maximum two sections. So if you take that first example, A if you take, so it's a cantilever problem, so with simple concentrated dough. So here from if I take this fixed support as the origin, this is x-axis, this is y-axis. So if you select a coordinate system, always distance we measure from left, taking this as the origin. Here we can take one section is enough, because if you take any point here all along this, the bending moment or shear force, it has the equation has to be same at that particular distance from left. So only one equation you will get either for shear force or bending moment. So only one section is enough. You have to take a section because x equals is that distance, either you can measure it from left to right or right to left, either towards left or right. So here I will take towards left. If you take towards left, then you have to find the support reactions first. So then only you have to start. Otherwise, if you take right section, you need not determine the support reaction. Straight away you can start doing your problem. Now here I will start from left intentionally so that I can first step in all these problems, you have to find the support reactions. You keep that as the starting point. Then after finding the support reaction, use the definition of shear force and bending moment, get the equations for sections, and you draw the bending moment diagram. So here, draw BMD and SFD for these problems. So here, if I take this first, I have to find the support reactions. Support reactions you have to find. For finding the support reactions, I told you how to apply equations of equilibrium. That is three equations of equilibrium: sigma h is 0, sigma v 0, and sigma m equals 0. If I apply here sigma h equals 0, you call this as AN, BN. So then HA will be 0. Here you get three reactions: HA, VA, and MA. Here I will take horizontal. So HA equals 0. So that means this reaction is 0. Then I will apply sigma V equals 0. I will get VA is equal to VA acting up and W acting down. So VA equals W, straight away can write it. Then if I apply sigma MA, or directly MA is equal to or sigma MA equals 0 if you take it. This MA is anti-clockwise negative minus MA, and this is W into L. Span is L. So W plus W into L clockwise. Because as per our same convention, if the moments are clockwise towards left, it is positive. So here this is positive, negative, this is also negative. The other equals 0, or MA equals minus W. Minus is this already is minus. So therefore, you take that section to find SFT and BMT. Okay, find the support reaction, you can find SFT and BMT. So this, consider a section x1, distance x from A. You can, only one section is enough, write the equation. So shear force at that section, Vx1, use it. As per definition, shear force at any section is defined as algebraic sum of all vertical forces towards left or right. Here I will take towards left. So without vertical forces towards left, it is only VA. So MA is the moment, HA is horizontal force, so only VA. So Vx1 is VA, which is acting up as per our sign convention. If shear force towards left acting up, positive. So this is positive. VA equal, Vx1 is VA, which is nothing but W. And this holds good for x equals 0 to x equals L. X equals 0 to x equals L. Same equation. At all these points, Vx1 is W only. It is of the form y equals constant. There is no x involved. That means shear force is constant. Right? It is one horizontal line. It is not straight line. It is just a horizontal line, constant. Right? All same ordinates. Then Mx1 is equal to, this is anticlockwise minus MA, that already is, that is Mx1 is minus MA, that is minus WL. It is Hagi.
VA into
Algebraic sum of all that.
That
Then
VA
of
into
course, Mx minus MA, then plus VA into
X.
X. VA into X is moment like this.
Yes, sir.
Clockwise, positive. Here, anti-clockwise.
Yes, sir.
So this is nothing but VA is W X minus MA is W L. So this is your moment equation. This is shear equation. This holds good between 0 and 0 equal to. Right? Now you can plot the shear force and bending moment diagram. We are measuring the distance from A point. So this is the equation. So you start at a horizontal line. Shear force, upwards we take positive, down we take negative. So here shear force diagram at x equals 0, that is at this point, it is W itself, right? Positive. It is W by plot. And x is equal to L, it is again W. So that is this. Here also it is from here to here. It is So this is your shear force diagram from point A to point B. This is the equation at any section. X equals 0 to x equals L. You find out and plot. Similarly, bending moment diagram at x equals 0, it is minus WL. I have plotted down. It is minus WL. At x is equal to L, it is WL minus WL. It is 0. So here to here it is 0. And this equation is of the form y equals mx plus c. It is straight line. So naturally this to this, it is straight line. So this is negative. That's the principle. How to draw bending moment shear force diagram for given loading. You have to go on getting this selecting section first, then getting the equation, observing the equation, whether it is constant form or straight line variation form or second degree variation form. So in that section you plot it. Get at one end of the starting of the section, ending of the section, get the value, join them by straight line or constant or curve form depending upon that equation in that segment. You will get either shear force or bending. That is as simple as that. So then if you take B on same lines, you will get here W L, of course. So if you take a section, these reactions, here this will be W into L, and moment, here you will get W L into L by 2. That is W L squared by 2, and horizontal reaction will be 0. Then if you take any section, so you will get dx at that section as W L and mx as W L yes, minus
Wx into x by 2.
squared by 2. Like that. So if you plot at x equals 0, it is plus WL. And again at x is equal to 0, WL, x equals L. No, at x. This is WL minus WX. Because algebraic sum of all vertical loads. This is one vertical load. Reaction also I have to take, that is WL positive. This is W into X, that is down. So this equation is y equals mx plus c, constant. Right? So it is straight line. When x is equal to 0, it is WL. When x is equal to L, it is WL minus WL.
0.
It is 0. From here to here, it is straight line. So this is positive. This is the shear force diagram. Bending moment diagram on same line. At x equals 0, it is minus WL squared by 2. I will plot it down. WL squared by 2 minus. Then at x is equal to L, it is WL squared minus WL squared by 2. And here,
WL squared by 2.
W, this is WL into
WL square.
Oh, this is sorry. This equation is WLX minus WX squared by 2. WX into X by 2. That is the equation. So when X is equal to 0, it is
0.
0. Not 0. Oh, sorry. WX squared by 2 minus WX squared by 2 also. All the three will come.
Yes, sir.
Moment minus WL squared by 2. This is WL into X. Due to this is WX squared by If you take algebraic sum of moment, moment due to this reaction, this load. What is this? This is due to this reaction, this is due to this load, this is this moment. All the three are. When x is equal to 0, it
Minus
is 0
WL
here,
square
0 here, it is minus
WL square.
WL squared by 2. Then, when x is equal to n, it is WL square minus WL square by 2. That is,
WL square by 2.
this is also minus WL square by 2. WL square by 2 minus WL square by 2. It is minus WL square. This is WL square. It is 0. And the equation is, here it is second degree. And here it is square with respect to the distance. Square. So where this is of the form y equals ax square plus bx plus c. It is not just y equals c or y equals mx plus c. That form. It is y equals ax square plus bx plus c form. It is parabolic or second degree curve. Curve, we can just show it as curve instead of a straight line. So this is negative. This is your bending moment. That's all the principle. Right? Next, if you take C, so where moment is there, that is very simple case. So again, here H reaction is 0, vertical reaction also has to be 0 because sigma v equals 0 if you apply V 0 and m equals 0 gives this moment is like this m, here it has to be opposite. Now this is perfectly in equilibrium. Sigma h is 0, sigma v is 0, sigma m is 0. That the moment you determine the reaction, make sure it satisfies equilibrium equation. Then only one section is enough at a distance x. So if you take Vx, that is equal to my Vx is 0 and Mx is equal to minus M because it is anticlockwise. Because it is like this,
Yes,
it
sir.
is negative. So therefore, here shear force will be just 0 throughout. Shear force diagram is 0 and bending moment diagram, here it is minus m, here again minus m only. So here it is minus m, y equals c form, it is constant, here to here constant. Here. You have to be very careful in moments. So that particular part is over. How to draw the bending moment. You take simply supported beam. If you take simply supported beam one by one, the first problem if you take here, first find the reaction. You call this point as A, B, C. First step is you find reaction. You apply three equations. Here you will get vertical reaction, horizontal reaction, HA, VA. You will get as reaction. Here you will get only vertical reaction. I showed you already. In case of roller, only one vertical reaction, H, two reactions, horizontal, vertical. Fixed support, all the three were there. So if you apply sigma H equals 0, you will get HA is equal to 0. There is no horizontal force at all. Then if you take sigma MA 0, moment about A, then this VB into L, it is like this, anti-clockwise. Then this W into A, which is clockwise. And these two will pass through A itself, it will not give. Now we can attach sine you take clockwise positive, then this will be negative, this will be positive. So if you do like this, then it is easy. Algebraic sum of all moments 0. And with this side convention, then you will get R equals 0, VB equals WA by L. So VB is WA by L. Then if you take sigma V0, then VA acting up plus VB acting up. Always we take reaction to start with positive direction equals 0. So here he equals minus W or plus W which is acting down equals 0. This is sum of all vertical forces. These are all acting up, this is acting down. Now you attach sign, upwards positive, VA positive, VB positive, this is negative 0. So VA you have, VB you have determined, so VA equals W minus WA by L or W into
1 minus
L minus A by L. This L minus A is nothing but B, that is WB by L. This I have simplified WB by. So then you can take two sections, one section here, another from this to this. Here, the moment you plot is another section. Two sections, you can take it, x1, x2, measure the distance x from left here, from here, from right. And take here slightly change from left to right, right to left. So A to C, B to C, so that the entire wavelength will be covered. So you write the equation for shear force Ex1. Take towards left because I am measuring the distance from left. Algebraic sum of all vertical force is only this. This is horizontal. So it is only acting up towards left side. It is positive as per our same convention. So this is VA itself, that is WB by L. Then Mx1 is this VA into X. This will not give any moment. It is only VA into X. It gives clockwise moment like that. So which is positive. So it is Vx into positive, that is WBX by L. WB by L into X. So this is of the form y equals C only, that's constant. Here, this is y equals mx. It's a straight line.
Straight line.
That's all. So you plot. You plot Vx this holds good between 0 less than x less than a, 0 to a. This also 0 to a. Then 0 to b is this equation that we take next. Here when x equals 0, it is WB by L positive. WB by L. When x is equal to a, it is WAB by. Now when x equals a, it is also WB by L only. Here it is WB by L. So it is positive. This is SFT from A to C. C to B, you can take another Vx2. I am measuring distance from x. Vx2 is just WA by L. So when x equals 0, it is 0. When x is equal to b, W A by L only. So it is again W, because here this is acting up towards right side. And acting up is negative. Because towards right side, acting down is positive as per our same convention. So this I will plot it down. W A by L. Here X is equal to 0, X equals B also, is same thing from here to here. This. So this is W A by L, here W B by L. So at this point, it is W A by L plus W B by L. That is W by L into A plus B. That is A plus B is L.
W.
So it is W. So this is your yes. That's as simple as that. Similarly, MX2 is this W A by L into X. This is clockwise. This side, so it is positive.
Anti-clockwise, positive.
Positive. So when X is equal to 0, it is that will plot it and see. So this is effective over bending moment diagram. So for this portion, when X equals 0, it is 0. When X is equal to B at this point, X equals 0 to B.
WAB by
That is WAB by
L.
L. So this side, it is positive. Positive means I have to plot it to the top. Here it is 0, here it is WAB by L. WA by L into
B.
Next, if you take this equation, this side, when X equals 0, it is 0. When X equals A, it is again WAB by L. Here it is. That's this is the one. Like that concentrated load and that moment you can try. So for this you will get parabolic variation because it will be, the equation will be X square, any moment equation. It is like that. And there also it is, you have to find the reactions here. So for this case, for finding the reaction, sigma h equals 0 will give this. So if you take moment about this point, then this VA into L is equal to M. So therefore, this will be, VA will be M by L. Then you have to satisfy sigma V equals 0. So this is acting up here, this has to be acting down. The two vertical reactions you have to find out. Whenever there is moment, you will get the vertical reaction. Then only one section is enough. Take Vx, that is M by L itself, and Mx equals Mx by M. We can plot. When x equals 0, this holds good between x equals 0 to x equals L, this also. When x equals 0, this VA is M by L itself. When x equals L also, M by L. So the shear force diagram is this M by L. This is S of D. And bending moment diagram, here when x equals 0, it is 0. When x is equal to L, it is
0.
M. It is M positive, right? So naturally, at that point, so this is what that is for this case. So this you can try, you get like this. So bending moment diagram. So that takes care of simple cases. Then combination of this. Combination of this, as usual, you may need number of sections. Each section you have to get equation like this: Vx1, Mx1, Vx2, Mx2. Observe that equation whether it is constant form or straight line form or second degree form. Go on plotting as I did in this case, from here to here, here to here, like that. So you get result. So that we can take one or two examples and proceed.